Okay, so good morning, everyone. Can you see the whiteboard?
Yes.
Okay. So before we move forward, let's complete the problem that we were considering last time. It is the problem number 2 in the list of problems that you have on Canvas. So we wanted to dilute a solution of hydrochloric acid. And if you remember, we individuated input and outputs and figured out that outputs are the level in the tank at the outlet acid concentration, under the hypothesis that the system is perfectly isothermal, and we also discussed the limitations of this. Now, as promised, I want to show you in another way that the outputs are CaO and H, because, as we mentioned, the outputs are basically the variables that you can get when you solve the mathematical model for the system. Let me show you an example and you will understand what I mean. So this is an isothermal system. Temperature is perfectly constant. We don't need the energy balance. So what we need is just the mass balance. And how many mass balances are possible for this system? 2, because we have 2 components, water and acid. As usual, we proceed with the total mass balance because it's convenient. And then eventually we will write the mass balance or the mole balance for the acid, for example. The total mass balance says that dV in the T, the instantaneous change of volume, is basically VA dot plus VW dot minus VO dot. And so here V is the unknown, but you know that V, the volume, is the cross-section area times the level. So if you are happier, you can write this as A, the cross-section area, dH over dt. So you know VA dot is an input, you know VW dot is an input, you know VO dot because is an input. There is a valve, is a manipulated variable. And so from this equation, you get V, or alternatively, if you know the cross-section area, you get H, that indeed is one of the outputs. Make sense for everyone?
Yes.
So now your question could be, what if there is no valve here? If there is no valve in the outlet, obviously, no valve means that VO dot is now an input or is an output?
It's an output.
Is an output. And so, what if I do not have a valve? No problem. Simply, if here you don't have anything to control the outlet flux, no valve, no pump, anything, we know from the Bernoulli's equation that, you know, this VO outlet, VO dot, is a constant alpha times the square root of H. Simply. So we solve again this equation. We find H, and once we know H and we know alpha, we automatically calculate VO dot, which is an output in this case. Make sense for everyone?
Yes.
Now, this is good, but it's not enough. We have a second equation, the mole balance, for example, for the acid. So the instantaneous change of the number of moles of acid is NaI, is the molar flow rate of acid entering the system with this stream. This other stream is just pure water, so there is no acid there. So minus NaO dot. The instantaneous change in the number of moles of acid is exactly the inlet molar flow rate minus the outlet molar flow rate. And now we have to proceed as we did for a perfectly mixed system. The number of moles can be expressed as the concentration times the volume. And so we have here V dCA in dt plus Ca dV in dt, exactly as we saw for a CSTR reactor, because Na is CaV. And this will be equal to what? To VA dot CAI minus VO dot CAO, I should write. However, CAO, the outlet concentration, is exactly the same concentration as in the reactor that we call the Ca. So I can remove the subscript O. Makes sense for everyone?
Yes.
Now, simply, as we did for the CSTR and for many other systems that are perfectly mixed, and so you should be familiar with this, we have to replace here the total mass balance that we wrote before. And so, V dCA in dt plus Ca dV in dt, based on the total mass balance that we wrote before, is VA dot plus VW dot minus VO dot. And this will be VA CAI dot minus VO dot CA. Just replace this term. So let's develop this product. VA dot CA plus VW dot CA minus VO dot CA equal to VA dot CAI minus VO dot CA. VO dot minus VO dot CA and minus VO dot CA will cancel out, exactly as happened in the CSTR and in other perfectly mixed systems. And so it turns out that this volume derivative of Ca into T is equal to VA dot CAI minus Ca. I'm just coupling together this term and this term minus VW dot Ca. And so V is known because you calculated this from the previous equation. VA dot is known, VW dot is known, CAI is known. The sole unknown here that you can retrieve is Ca, is the concentration in the reactor that is basically also the outlet concentration CaO, because the system is perfectly mixed. And so the outputs are exactly the variables that you get if you solve the mathematical model that governs the system. Make sense for everyone?
Yes. Can I ask a question?
Sure.
So this, like the reason we just did this was to show that like the outputs we get when we look at the diagram would be the same as the outputs if we solve the equation. Like they should give us the same.
Yeah.
Okay.
It's just to use a more analytical method.
Yes. Okay, thank you.
No problem. No problem. It's just to convince you that the analysis of the diagram provides the same result as the analytical procedure, as should be every time. There is never the possibility for confusion. Okay. And now we can move to the next problem. Again, if there are questions, just ask. The fact that we are in remote, that is not a sign that you have to keep your doubt for you. If you have questions, ask. Okay. Now, let's move to the problem number 3. There is an open microphone, please. Problem number 3. We have a differential equation. Given this differential equation, we need to solve the equation using the Laplace method. So first question first. Is this equation linear, or should we linearize this?
It's already linear.
Is linear, is linear. Now, second question, is this equation written in the deviation variable form?
No.
Why? That's correct. Is not written in the deviation variable form. And why? From what lets you say that is not?
Because the like at 0, in deviation variable form, if we plugged in 0, then we would get 0 out.
That's perfect. That's right. If this equation was written in the deviation variable form, the initial condition would be y calculated at the time 0 would be equal to 0. And instead, we have 1 instead of 0. So the initial value is not 0, is different from 0, is 1. So it is not written in the deviation variable form. However, we can proceed. We can proceed with the Laplace, but we have to pay attention. We have to pay attention. So is linear, we can apply the Laplace transformation and transform this into an algebraic equation. So Laplace transform of the sum is the sum of the Laplace transforms. So 5 times the Laplace transform of this derivative. So will be S times y capitalized, where y capitalized is the Laplace transform of y. I'm just applying the formula. So if you don't remember the formula, make sure you have the table with you. Minus y non-capitalized, minus the original function calculated in 0. Formula that gives the transform of a derivative, plus 4 times the Laplace transform of y, equal to 2 over s, Laplace transform of a constant. And now you have to pay attention, because the system is not written in the deviation variable form. If the system is written in the deviation variable form, this term here that I'm highlighting now would be equal to 0. Since the system is not written in the deviation variable form, we have just to keep in mind that this is not 0, but is 1, as you can see in the initial condition. Make sense?
Yes.
Okay. So this becomes 5, which multiplies sy minus 1 plus 4y equal to 2 over s. So 5sy minus 5 plus 4y equal to 2 over s. And now I have basically to isolate y. I have to calculate y. So I collect this term and this term together, and I bring this minus 5 from the other side. Simply, y is equal to 5s plus 2 divided s divided 5s plus 4. So does this answer our question? No, because yes, we found y, but we found y in the Laplace domain. We don't need y in the Laplace domain. We need y into the time domain. So what should I do now?
Anti-transform it?
Anti-transform back to the time domain. So should I really interrogate the Heaviside theorems here? Not really. When you see these kind of expressions, it is sufficient a small manipulation to make things work in an easier way. Indeed, I can rewrite this in the following shape by breaking this sum. So this will be 5s divided s 5s plus 4 plus 2 divided s 5s plus 4. And this s and this s will cancel out, which is very convenient. Now, if you look to your tables, can you recognize the similar expressions in your tables directly to make the anti-transformation? I think so. And let's see this together. So you can see in the table that the anti-transformed of 1 divided s plus a is equal to the exponential of minus at. So does this expression here, 1 over s plus a, resembles this one? Yes or not?
Totally.
We have just to do some manipulation. And remember that the anti-transformed of the function a divided s tau s plus 1 is equal to a 1 minus exponential of minus t over tau. Does this expression in square brackets resembles this expression here?
Yes.
I think so. We have just to do some manipulation. So I simply can rewrite this in the following way. If divide everything by 5, numerator and denominator, this will become 1 divided s plus 4 over 5, which is exactly this expression here. And to make this more similar to this, I have to let this plus 4 disappear and become plus 1. So I can collect 4 out of the bracket and get something like this. Make sense for everyone?
Yes.
2 divided 4 is directly 1/2. And now this expression is really equal to this. So I can immediately anti-transform and get y function of time, which is what I'm looking for. And so I get the anti-transform of this exponential of minus 5 over 4 time plus 1/2, 1 minus exponential of minus 4 over 5 t. So just adjust a little bit, manipulate, and write in a more, in a nicer way to get 1/2 that multiplies 1 plus the exponential of minus 40 over 5. So this is the solution of the original differential equation calculated using the Laplace method. So, do you understand? Make sense for everyone?
Yes, sir.
Yes.
Okay. So please, we need to become familiar with this. So if you have doubts, if you have questions, just ask for office hours. When you have these, relatively simple expressions, you don't really need to interrogate the EV-side method. Now, the problem number 4 is basically a problem that we already solved in the classroom when we introduced the EV-side theorems. So you already have the solution for the problem number 4. So we can move directly to the problem number 5, which starts to be a little bit more complicated, but not that much. The sole difference is that now we have a system of differential equations instead of a single differential equation. And we have also something to discuss here. So the two equations are the following. Derivative of y1 with respect to time is equal to 2y1 plus 3y2 plus 1. The derivative of y2 with respect to time is equal to 2y1 plus y2 plus exponential of time. y1 calculated in 0 is 0. y2 calculated in 0 is 0. So, first question first. Is this a system of differential equations linear or nonlinear?
Non-linear.
And here I am picking on you guys. Here I really wanted to joke with you. Look very well. Look very well. And, have with you the definition of differential equation that I gave you a while ago. The definition of linear differentiation that I gave you a while ago. So this equation, in particular, for the equation number 1, we do not have doubts. That really looks linear. The problem is probably the second one, but this is linear because I know that there is an exponential function, but this is the exponential of time. It's not the exponential of y2. This would be non-linear if this one would be the exponential of y2 or the exponential of y1. The exponential of the dependent variable. This is the exponential of the independent variable, exponential of time. Therefore, this is linear. Make sense for everyone?
Yes.
So, I did this intentionally, indeed. I used this equation intentionally, just to challenge you and let you reflect on this. This is linear, because this is exponential of time, not exponential of y1 or y2. In that case, it would be nonlinear. But since here we have the exponential of the independent variable, the exponential of time, this is linear. Questions? No, okay. So, second question, as usual, is this system written in the deviation variable form or not? Is in the deviation variable form or not?
Yes.
Yes, because the initial values are both 0. Make sense for everyone?
Question.
Yes.
If the initial condition is equal to 0, does that always mean it's in the deviated variable form?
Mm-hmm.
Okay.
Yep.
Just to play the devil's advocate, couldn't there be an equation that was not in the deviated variable form that still happened to have the output of 0?
That might be fortuitous, but normally in the applications is not, because for us normally the initial steady state, for us the initial condition is the original steady state, and generally it will be different from 0.
Yes. Okay.
The absolute value, I mean. Make sense?
Yeah, that does. Thank you.
Mm-hmm. No problem. So if you have any questions, please ask. So we have said we can transform with the Laplace. We have just to do this a couple of times because we have 2 equations. So first, S times the y1 capitalized. y1 capitalized is the transformed of the original y1 variable minus y1 calculated in 0 is equal to 2y1 plus 3y2 plus 1 over s. S y2 minus y2 calculated in 0 will be equal to 2y1 plus y2 plus 1 over s minus 1, because the transform of the exponential function is 1 divided s minus 1. So now these terms are both 0, so I don't have to worry about this. And so basically we have sy1 minus 2y1 is equal to 3y2 plus 1 over s. And sy2 minus 2, sorry, sy2 minus y2 will be equal to 2y1 plus 1 over s minus 1. Make sense? Yes or no? Okay. So now what I have to do is, for example, retrieve s1 from this and replace in the second, because we want to find y1 function of s and y2 function of s. We want to find the two outputs, the two unknowns in the Laplace domain. And so from the first, I get s minus 2y1 equal to 3sy2 plus 1 over s. And so y1 is 3sy2 plus 1 divided s times s minus 2. So now y1 is expressed as a function of s and y2. So what I have to do is simply replace here in the second one. Make sense?
Yes.
Okay. Now let me skip a little bit of algebraic steps, because you can do them by yourself. And basically we get y1 and y2 in the Laplace domain as follows. So y1 is s squared plus s plus 1 divided s minus 1, s squared minus 3s minus 4. y2 will be equal to s2 squared minus 2, and the denominator is the same. So now we got basically an answer to our problem, but this is not a real answer, because yes, we got y1 and y2, but they are in the Laplace domain. We want them in the time domain. So what should I do now?
Anti-transform.
So do you see this anti-transformation that easy as before? Probably not. Probably here the situation is a little bit more complicated, and probably here we have to interrogate the Heaviside theorems. So what is the first step when we apply the Heaviside theorems? We have to find the poles, the zeros of the denominator, and then we have to see in which situation we are. So for sure, a pole is 0, a pole is 1, and then we have this quadratic expression that needs to be decomposed so that we can find the other two poles. So we have to find these other two poles. So delta is 9 plus 16 is 25. And so basically the poles are 4 and minus 1. And so I can decompose this factor in s minus 4, s plus 1. And so basically now we have as poles clearly 0, clearly 1, clearly 4, and clearly minus 1. Does everyone agree with this? So in which situation we are if we want to apply the Heaviside theorem?
The
The first
first.
theorem?
First. because all of these are real, no complex numbers. All of these are real, and all of them are distincts. There are no repeated poles. And so we can apply the first Heaviside theorem. Unfortunately, we have to do this twice because we have to apply, the Heaviside theorem to anti-transform y1 and anti-transform y2. So let's start with y1. So we want to anti-transform this to the time domain to get y1 function of time, knowing that the poles are 0, 1, 4, and -1. So contribution of the first pole, s equal to 0. So the first contribution to y1 is what we call y11. So first Heaviside theorem, numerator calculated in 0, 1, divided. So which term should I suppress now at the denominator?
S?
S. So let's suppress the contribution of S, and then we have to calculate the denominator in 0. So -1 times -4 times 1 exponential of 0t. And this will give you clearly 1/4. Okay? So second pole, S equal to 1. So the second contribution to y1 is y12. So numerator calculated in 1, which is 3, divided. So which contribution should I suppress now from the denominator?
S minus 1.
S minus 1. So 1 times S minus 1, that's suppressed, times this calculated in 1, times this calculated in 1. So time -3, time 2, exponential of time. And this will give you -1/2 exponential of time. So let me highlight the single contributions. Now contribution of the pole S equal to 4. So y13, the third contribution, will be the numerator calculated in 4, which is 16 plus 4, 20 plus 1, 21. Which contribution should I remove now from the denominator?
S minus
S
4.
minus 4.
S minus 4. So we have 4 times 4 minus 1, 3, and then S minus 4 that we suppress, and 4 plus 1 that goes to 5, exponential of 4t. So is 7 over 20 exponential of 4t. And finally, let me move up. Contribution of the pole S minus 1, so is the fourth contribution, S14. So will be the numerator calculated in -1, which means 1. Which term should I suppress now at the denominator?
S plus 1.
S plus 1. So we have -1 times -1 minus 1 minus 2, -1 minus 4 minus 5, S plus 1 that I suppress, exponential of -t, which goes to -1/10 exponential of -t. So now to get y1 function of time, to get basically the first output function of time, I have just to sum algebraically all these 4 contributions. 4 contributions because we have 4 poles. So let me just wrap up, sum them together, and give you the solution for the term y1. So y1, function of time, is equal to 1/4 minus 1/2 exponential of times plus 7/20 exponential of 4 time minus 1/10 exponential of minus t. And this is the first solution. Now we have to do the same, we have to repeat the same calculation for y2. Make sense for everyone?
Yes.
Okay. Let me just rewrite y2. So the numerator is different, s squared minus 2. We want to get y2 function of times, and the poles are still 0, 1, 4, minus 1. So we have to repeat everything over new for the second contribution. So s equal to 0. First contribution to y2. y2, 1 is the contribution associated to the pole 0. And so basically we have now minus 2. Which contribution should I remove at the denominator?
Yes.
S. And so basically we have basically minus 1 times minus 4 times 1 exponential at 0 time, which goes to minus 1/2. Minus 1/2. S equal to 1. So y2, second contribution. Numerator calculated in 1. So minus 1 divided 1. And then I have to suppress the contribution s minus 1. And then 1 minus 4, 1 plus 1, exponential of time. 1/6 exponential of time. Very easy. S equal to 4. So y2, third contribution, will be the numerator calculated in 4. So 16 minus 2 goes to 14. So 4 times 4 minus 1. Then I suppress the term s minus 4, 4 plus 1, exponential of 4 time, and this gives 7/30 exponential of 4 time. Now s equal to minus 1, so y2, 4, fourth contribution, will be the numerator calculated in minus 1. So minus 1. I have to remove from the denominator the term s, the factor, sorry, s plus 1. So we have minus 1, minus 1, minus 1, minus 1, minus 4, exponential of minus time. That goes to 1/10 exponential of minus time. And so now I have to just sum these contributions together. And in this way, I get y2, function of time, which is minus 1/2 plus 1/6 exponential of time, plus 7/30 exponential of 4 time, plus 1/10 exponential of minus time. And this, coupled with the y1, is one of the 2 solutions of this differential equation. Make sense?
Yes.
So as you see, the procedure is always the same. Now, a little bit of a critical analysis. You know, the system was written in the deviation variable form. So let me polish a little bit here. So now, guys, a little bit of I want to challenge you another time. We get y1 and y2 function of time. But my question for you is, are these the absolute values of y1 and y2?
No.
No. What do they represent?
The deviation from our original steady state.
Yes, that's correct. These are not the absolute values of y1 and y2. They are simply the deviation from the original steady state. So these should be y1 and y2 with this symbol. They are, again, the initial value of temperature in the oven is 400 Fahrenheit. And then you rise the temperature at 450 Fahrenheit. These are not 450 Fahrenheit, but is the deviation, which is 50 Fahrenheit. Keep these in mind. They are not absolute values. They are deviations. Now, problem number 6. Problem number 6. Because at the end of the story here, we are not interested in knowing what is the final temperature in the reactor, what is the final concentration in the reactor. We are interested in knowing how the temperature in the reactor, how the concentration in the reactor deviate from the expected values. So problem number 6 is given a function f in the Laplace domain, which is s minus 1 times s plus 1 divided s times s plus 3 times s minus 4. So, it's a very complicated system. This is a third order system. This could be, for example, a series of 3 isothermal CSTR reactors with the first order kinetics, as we will see soon. So we want to find the value of the function f, function of time, at the time equal to 0. So we have a function in the Laplace domain. We want to find the value of the corresponding function in the time domain at the time equal to 0. So now what I propose you is, let's anti-transform this back to the time domain, and once we get f, we just calculate this value in 0. Would you like to do so? Honestly, would you like to do so? Or perhaps we can do something else.
Could you use the initial value theorem?
That's right. That's right. So this is a typical situation. This is a typical situation where, I'm asking you to go to Austin, Texas. And basically you have two options. You have a very straight highway to go, or you may go to Memphis, and then Atlanta, and then New Orleans, and then Austin. So don't pick the long road. Pick the shorter road. You don't even need to anti-transform this back to the time domain, because as Taylor mentioned, we have the initial value theorem. That's what that theorem is for. So you don't really need to, embark into long calculations if you don't really need to do so. And so just remember, that's why it's important that you know the theory. The limit for time going to 0 of f function of time is the limit of s going to infinity of s time function in the Laplace domain. So, why complicate things when things are simpler? This is what we are interested in. This is what I'm asking you to calculate. And so you can do this calculation simply by moving the calculation on the corresponding Laplace transform that you already have. So basically, f calculated at the time 0 will be the limit for s going to infinity of s time this function. So s minus 1, s plus 1, divided s plus 3, divided s minus 4. Makes sense for everyone?
Yes.
So simply, this is what engineers have to do. This is what engineers are for. Engineers are to simplify problems, not to complicate problems. So this is s squared minus 1 divided s squared minus s minus 12. So we have to calculate the limit for s going to infinity of this quantity. In this way, this is infinity over infinity. So just remember what you know, and let's collect the highest degree term. If s, these and these will cancel. If s goes to infinity, these terms will go to 0, and so you have 1 over 1. Very simply. So, is that clear?
Yes.
Okay. Guys, the more calculations you do, the more chances you have to make mistakes. So, do less calculations. Less is more. Obviously, if you want to anti-transform, it's up to you. That works. Problem number 7. And now, let's start to dive into something that we will really consider a lot of times. A process is described by the following differential equation. It could be anything. It could be a reactor, it could be a heat exchanger, anything. Second time derivative of y plus 5 time derivative of y plus 6y equal to f. So a process is described by this differential equation. So in each case, we know that y0 is equal to 0 and f0 is equal to 0 and dy over dt calculated in 0 is equal to 0. Is this a linear differential equation?
Yes.
Yes. Is that written in the deviation variable form?
Yes.
Absolutely. Absolutely. It's linear and is written in the deviation variable form. So now, guys, remember what I told you last time when we introduced the transfer function. Let's consider this equation represents a unit, a chemical unit, whatever. Who is the output?
F.
The output.
Why?
That's right. That's right. So, Y is the output and F is the input. You remember we discussed this last time. Y is the output, F is the input, and this is the process. So how we do normally represent processes? By their transfer function. The transfer function is the ID of any process. And indeed, the question here is develop a transfer function that describes the effect of the input f on the output y. So we have to find the transfer function. Now, very clearly, we have to find the g, the transfer function of this process. So how would you proceed? So is the transfer function in the time domain or in the Laplace domain?
Laplace.
Laplace. So we have to transform. There is no way. And so let's go ahead and transform. Is written in the deviation variable form. So this is s squared y is the transform of the second derivative plus 5sy, the transform of the first derivative, plus 6y equal to f. Y capitalized is the transform of y. F capitalized is the transform of s. So basically, we are moving the problem from the time domain to the Laplace domain. And basically, f non-capitalized becomes f capitalized, the output y non-capitalized becomes y capitalized, and the process becomes the transfer function. And this is what we call block diagram, as we see last time, is the block diagram. So I can collect y, s squared plus 5s plus 6 equal to f. Okay, and now what? Well, if I want to do something, I have to know the definition of what I'm doing. That's why I need to know the theory. And if I don't know the theory, I cannot do anything. So, guys, definition of transfer function. Please, go ahead and give me the definition of transfer function.
F minus y?
Sorry?
F minus y?
F minus 1.
Y.
Y? No, is y over f. Is the Laplace transform of the output in the deviation variable form divided the Laplace transform of the input in the deviation variable form is y over f, which is clearly 1 divided s squared plus 5s plus 6. Make sense for everyone?
Yes.
Now, critical analysis as usual. As usual, we should never, ever accept numbers as they are. We are smart and we have to criticize. Which is the order of this transfer function?
2.
Sorry?
The second order?
Second order. Yeah, sorry, I didn't hear. Second order. Is this, does this make sense? Can we accept here a second order transfer function?
Yes.
Why?
Because the original differential equation was second order?
That's right. Second order system, second order transfer function. So makes perfectly sense. Now, coefficients of the denominator. They are exactly the same coefficients 1, 5, and 6 that we have in the original differential equation. So makes sense. Makes sense. Now, let's consider a disturbance hits the system. How can we find the response? And we will see this next time. Simple. The response y will be the transfer function g that we have time the Laplace transform of the disturbance. And that's it. And that's it. So if you have a first order system and you get a third order transfer function, please check, because this is not possible. Second example. Second derivative of y with respect to time plus 3 derivative of y with respect to time is equal to f. So f is the input in the time domain, y is the output in the time domain. Obviously, the equation is linear. Obviously, is written in the deviation variable form. So f is not absolute value, but is the deviation of the input from the original value. Y is the deviation of the output from the original value. We need a transfer function. So we need a function g that connects the Laplace transform of the input to the Laplace transform of the output. And g is clearly y over f. So to find g, the transfer function, we have to transform. So s squared y plus 3sy equal to f, capitalized because we are in the Laplace domain. So I collect y, and then y over f, which is g, is clearly equal to 1 over s squared plus 3s. Second order process, second order differential equations. Coefficients here are 1 and 3. Coefficients here are 1 and 3. There is no coefficient. There is no coefficient because here there is no coefficient. Make sense?
Yes.
So this is what we have to do every single time. Just let's consider another example. There are, I think, 6 or 7 examples there, but all of them are really the same. So we have again, the process is linear, is written in the deviation variable form. So to get the transfer function, I need just to transform. So s squared y plus 4sy plus 4y is equal to the transform of f. So I collect y, s squared plus 4s plus 4 equal to f. And so y over f, which is the transfer function, is 1 divided s squared plus 4s plus 4. So now guys, let's start to reconnect things together to get prepared for next class on Thursday. This is the transfer function of this process. Look at the denominator. Can you recognize anything here?
The order and coefficients are the same as the original equation.
Mm-hmm. And in particular, the denominator is the square of s plus 2. Make sense?
Yes.
So, which are the poles here? The poles are -2 and -2. So we have a repeated pole. Now, my question for you is, if I give a perturbation to this system, it could be whatever. If I give a perturbation to this system, would you expect an oscillating response or not? And if yes, why? If not, why?
Because we don't have complex poles?
That's right. That's right. So, see, we are not doing calculations. We are not doing calculations, but we can predict that, as Haley mentioned, this system will not oscillate. Will not oscillate because the poles are real and repeated, but they are real. They are still real. There is no complex pole. So for sure, if you give a perturbation to this system, for sure you won't observe any oscillation. Make sense for everyone?
Yes.
So now we have to reconnect all the parts. We have to reconnect all the parts of this theory that we are building up since August. And as you see, with no calculations, with no experiments, which would be very expensive and dangerous, we can simply predict. We can predict the response of a system based on a linear theory. So based on a few calculations. So just reflect a little bit on this, because next time we will formalize, we will formalize this. We will learn how to basically predict the response to any disturbance simply from the analysis of the transfer function and the Laplace transform of the E. So I will see you in a couple of days. In the meantime, don't forget that in 15 minutes, the homework has to be turned in. Stay safe, and I will talk to you soon. Bye-bye.
Thank you.
Bye.